Speaker we have today is a specialist in infrastructure, microservices, and observability. He's a very broad contributor to open source and is currently working as a staff software engineer at Datadog, also formerly of Red Hat. So would you please give a big hand for unleashing the Go toolchain to Kemal Akkoyun.
So, hello everyone. Today we're gonna talk about Go toolchain and an open source tool that we are building. So, who am I? I'm an open source software engineer. I've been working on infrastructure tooling around, I think, since 2017. When I joined Red Hat, I started working on CNCF-based observability and distributed system tools, Prometheus, Kubernetes, whatnot. I'm also still a Prometheus maintainer, and I'm contributing to the OpenTelemetry. So, I work for a small startup called Datadog. At this point, I think we have 30K users, and we have, I think, like 8 out of 10 most prominent AI companies, whatnot. So, I had to do that. The shilling time is over, but do you know this mascot has a name? No. Yeah, I learned when I joined Datadog. Its name is Bits. So Datadog, Bits, pun intended. They really like dog puns inside. Yeah, dog pun meme is a thing. So, but like before we maybe continue, like if you're interested in working for Datadog, we are one of the most prolific contributors to the Go runtime after Google. So we have a couple of people constantly try to improve the Go tooling system, especially when it comes to tracer, profiling, whatnot, or the performance bits. So let's talk about first what makes Go great. For me, it's simplicity. And when it comes to simplicity, why it's important? Because most of the times we read the code, then we write it, or like compile it, and then the machine is executed. Machines doesn't care if the code is readable, if you run the linter, formatter, whatnot, but it's all about the cognitive load that you have. And that's why Go is great. I used to work as a Ruby on Rails engineer back in the day, and usually Ruby is a really nice language to work with. It's also simple to understand, but it's not simple to troubleshoot, right? So, but Go has everything. It's easy to read, understand, troubleshoot, simple to operate, because you can just build a single static binary and deploy it. So there's no magic. We can summarize it like that. Why this matters? Magic seems great while coding, but troubleshooting time, it's a mess. If any of you, if you ever work with Rails, you would understand this. So there's always a but, right? So let's roll back a little bit. Let's talk about 3 pillars of observability. People like that phrase. I think now we have the 4th one, profiling. Maybe we will continue adding more. But what we mean by that, to observe a process or service, we try to collect some signals. They are basically events or aggregated events. So logs, what you know, it's the easiest thing that you can do. Just log a line. This happened, that happened. When that happened, this was the thing that at hand, whatnot. And the metrics are some measurements. They are basically aggregations. So you measure something, what's happening else, like the current CPU usage, or like a histogram of the durations of the request that your application is serving right now. I'm a metrics guy, so even though I'm working for tracing right now, I think the metrics is the best signals out there, because it's cheap, it's easy to add, and you can take actions on top of that. You can build alerts for your services, and if your service is down, you can page someone, and you can do that based on the metrics in the cheapest way. But if you want to know more about your application, I don't know, network topologies where you are spending most of the time and what's happening when you are spending that time in that service. Like traces is your friend, basically. Traces give you the most of the things, but it's also the hardest to integrate into your systems because you may have different programming languages, different runtimes, different sort of services, and like context propagation is a problem. So to see the full life cycle of a request, for example, if you have an online HTTP or gRPC-based system, it's hard. Still, like to this day, I think it's a cultural thing that like hinders us to integrate with the traces. So how do we do these sort of instrumentation, right? So the manual way, we just write some code, right? Go away, it's simplified. This is an example of how we set up a tracing system. So these code samples are based on OpenTelemetry, so they're open source. So you create your provider, you create your exporter, and then finally you got your tracer, and then you pass around your tracer and start collecting traces. This is the most simplified way. But in real life, it looks like this. So you have, oops, I can't scroll. No? Ah, okay. You, first of all, import a bunch of packages. I don't know why they designed Go SDK like this, but it's hard to integrate, and you do stuff like propagators, metrics providers, logger provider, like I don't know what most of the things are. So, and then, yeah, after all these things, you have a functioning facilities to export traces out of your application. And then you got your tracer, and you pass it around. If you have a handler, and you would like to see the life cycle of a request, this is basically what you do. And rest is your business logic. So, it was Go. It's quite simple, but let's see how it happens in the Python, for example. Similar, maybe less code, because they have default way to get their tracers, and they have like fancy syntax, and then they have exceptions, are like easy to integrate. Let's see the same thing with Go. Yeah, it's not that bad. Right? You have all the facilities, maybe you record your errors, whatnot. So when you compare like this, that's okay. Yeah, we have a bootstrap code we need to do, but there's other ways to do that. Like we call it semi-automatic ways, which is like using annotations and decorators in Python terms, this is not OpenTelemetry, but in theory you can have tracers like that. But it's just an annotation and instrument this application, and boom, you have everything. Similar thing you can do with Java. Java allows annotations. So you can add an annotation, and you can start collecting your data. They even have like things like span attribute to the arguments that you have, and you can put those into your spans or like instrumentation code. For Go, it's still manual. Yeah, it's few lines of code, but the thing is, you need to do it everywhere. Like that's the problematic part. Every function that you would like to instrument, you need to put this boilerplate. But there is another way to do this, not in Go. In Python and Java and Ruby, basically zero code changes and you got everything. For Python, you install a package that comes with a bootstrapper, you do that, and then you just say, okay, OpenTelemetry instrument my Python application, and you got everything. Even like the function calls in between, so the in-process function calls, not just the HTTP request that you have. For Java, they have a jar. You install it, run your Java. Probably you have a container at this point, and you just like modify your container, and your application is instrumented. Works with all the popular frameworks and libraries. But with Go, we don't have anything special. We still write the code. No agent, no magic, just boilerplate. So some reality check. So the developer experience gap is real, especially for a company like Datadog, because like we have a lot of customers, they have like different environments, different languages, and they want to see everything in the same UI, or like they want to collect everything in the same bucket, basically. So the pain is real. So manual instrumentation means you need to write all those boilerplate code, remember to add the spans to the new code. Like maybe you have some team or component, they haven't started instrumenting their code, and then you have these gaps in your spans. You don't know what's going on there, but you technically know there is a service in there, but they haven't started instrumenting their code. Okay, you have the egress point and ingress point and the egress points, and you know, like, okay, this is the amount of time has passed between these requests, but what happens in between? It's hard to keep track of, and there's always the maintenance burden. Something changes, like especially OpenTelemetry SDK, it changes a lot. So you need to, whenever you would like to upgrade, you need to change the code. It always breaks. I don't remember an upgrade of OpenTelemetry SDK that I haven't broken my builds yet. So we assume what Go developers want. I don't know. They want the same experience, zero friction, automatic instrumentation, without any runtime overhead or manual code changes. So the question, like, how can we compete with all these runtimes? The Go runtime is by design simple, and we don't have JIT, we don't have like a way to rewrite the bytecode, we don't have even the bytecode, it's just compiled binary, right? So it's hard to get support from the runtime itself. So the challenge, we don't have annotations, no runtime code injection, we need to compile everything, so we need to find a way. Solution, Go has a hidden power, which is the key part of the talk. The toolchain is another Go program. So if you can modify any program, you can change things. So Go puts its magic in the tools, not the language runtime itself. So let's see some show of hands. I don't know, I don't see you, maybe you can shout as well. Have you ever heard of toolexec or used it? We can see a couple of hands, okay. So let's introduce toolexec. It's a flag in Go build, and it's basically one of the best kept secrets of Go. I don't think it's a secret at this point, but you can do funky stuff by hooking into toolexec. There were some other previous talks in the GopherCons. One was from Daniel Marti. He tried to obfuscate some code. Another talk from last year's GopherCon US. They tried to build their own code coverage tool, for example. So how we do this? We can intercept all the build phases of a Go program. So let's write a simple wrapper and see ourselves. It is just consume some command line arguments. And the first argument is the tool name, and the rest the args that it parses. And we're just going to like print them out. And we also let's, for sake of like doing something real, and let's capture the time and see what happens. So you build that binary, pass that flag to the Go build chain using toolexec flag, and you see lines like this. So there's a compile time, and it took 23 milliseconds. And there's a link command that is executed. And you can see what's going on, like how Go runtime it behaves. So technically, we can intercept all these calls. So, and we can see, observe what's going on. So intercept every tool call. Let's try to wrap each of these and see what we can do. By like doing these, like running and checking the logs, we can see that this is very simplified. The Go build time, it compiles the runtime compiles a bunch of packages, all the dependencies that you have to have that program. There is this phase of like parsing the source code, figuring out what it imports, like building a dependency graph and compiling everything, and in the end, linking everything together. I don't want to like focus on this part of the process, how Go build process works, but there's a really great talk from, I think, GopherCon UK 2022. Yeah, I learned a lot by like watching this talk. So if you want to dive deep, you can have a look. So let's say we want to target the compile step, right? It's just some matching the string. We know that that's what gets called to the toolexec. And then we can say, okay, handle compile time with the args and do something about it. Let's say we just want to care about the Go files. And from the Go files, we would like to do some analysis or some modification to those files. We can do that. So the next phase. Now we have all the source code that like funneling through, and we can hook into that. Let's talk about what we can do about it. Who here has ever written a linter or similar things? Couple of hands. All right. So Go has amazing facilities for parsing, transforming, and reasoning about the source code itself. Basically, you can do a lot of AST, asymptotic syntax tree manipulations. So, and yes, you cannot see what is like. Go has some intermediate representation as well. You can actually like see what it is generated as well. That you have facilities in the Go runtime with the packages. You can see what's the SSA output. You can see what is the AST output. Especially when you want to do like really advanced things, like, okay, I would like to check around what's going on with the locks, for example, and where do I acquire the lock? Do I actually like release that lock? The best place to observe those things is in the SSA, for example, and then there's a way to actually check that. There's a really nice linter called checklocks in the gvisor tool repo. It's not a standalone thing, but I've been playing with that, and I was amazed. Okay, we can actually statically check the logs, and we can see if we have already acquired this log. Okay. It was a sidetrack, but let's see what it gives, right? We can parse the source code into a syntax tree. We can walk and analyze. This is what linters does, right? They see a pattern, okay. Let's say you forgotten to handle an error, right? And they check, okay, there's a function that returns an error type interface, intertype value, and you are assigning that to an underscore. And you are not like doing any comparison to that, right? You can just like check the linter, find that pattern, and just like yell at the user, don't do that, right? But moreover, you can actually modify the code itself on the fly, right? You can match those patterns and then change the code. And then you can generate valid code, generate packages, and feed that into the Go build toolchain again. So, let's check how it looks, basically parsing the Go tree. This is a very simplified example. So you remember our analyze Go function from the previous toolchain hook command. Like we are checking that, converting that to a token set, parsing the file. If it fails, we return error. Oops. And then we try to find, for example, this is my tool is, all the declarations in this file, right? This is how you do it. Okay. We have a way to parse, gather some statistic, maybe just like the high-level stats, and we can just print them. But what if we want to do something more involved? We can actually walk the tree. There's a function called AST inspect. You can give, there's a function called, you can implement an interface called visitor. There's a function called walk, for example. You can walk the AST tree. You can have a little bit more involved, but you can also have the inspect, pass a closure, and check the nodes itself. So here, we will try to add annotations to Go code, right? We don't have annotations in Go, but let's say these are, but we have something equivalent to that. We call them directives, right? / Go link name, for example, or the build text that we have in the file. These are called directives. Like the Go itself, it uses that. Maybe you can say that, okay, don't inline this function. It exists, right? Let's follow the same pattern and try to have something like, okay, we would like to inject some log lines. Let's call it DD, Datadog, sorry, and then log, and then whenever we see that annotation or like a directive in the function, let's try to add log states in that. So for that, we need to find all the function declarations and then check if it has the log command. And then remove it, let's immediately clean it up, and we are going to inject logging, right? And has log command file, looks like, okay, there's file, you can extract the commands itself, find the comment group, do some string checks. Oops. Okay, didn't highlight that part. And check if the text contains dd.log, right? This is our investigation stage. One of the shortcomings of the standard library packages around the comments, you don't actually store the positions of the comments. So if you change the tree, add a bunch of lines, you lost track of the comments, and you can easily mess up the comments, not the code itself, because it's the AST, but the node, the comments that are associated to the correct node, you lose that information. There's already an open issue, and the Go team, they already acknowledged that. They would like to improve the standard library, but there is an open source version called DST, which stands for Dave's syntax tree, which helps you to keep track of the comments itself. So it's preferable. But for sake of simplicity, I didn't use that package. But there's an issue. They want to address that thing. So let's modify the AST itself and inject some log statements, right? How do we do that? This is a little bit ugly part, because we are building that actual AST. Okay, we want to add the start, and it needs to be an expression from the time now. You represent that. And then let's say we would like to add the slog info, and we do that. And we add the tokens. This is the thing that I would like to add. So it's a labor-intensive code. And then you want to add the defer statement, because you would like to record the function exit duration. And then, yeah. Then I forgot to highlight that part. And then you add that function body list, append all these statements to the function that we are modifying. And what happens that, okay, this is a valid syntax tree, and then you just spit out the code, run the Go format in the code, and you get something predictable. So from linter to a modifying code, we now can generate more stuff, right? That was about the modifying the code. Maybe we would like to import some packages, generate some packages, add some files. There is also another open source package. This is from Golang.x repo called AST utils. It is the interface that I previously mentioned, the visitor interface or the inspect interface. They don't let you to modify the node in place. You can just modify the children of the node, and because it's not a pointer, and it's they realize that they made a mistake in the API, but this is Go, it's backwards compatible. So that's why there's this AST util package exists. It's cleaner to modify the nodes. So we use that. We had a named import. We don't need that, but I just wanted to demonstrate there's the function of that, because slog is slog. But then We write and generate a file. Now we have a file that all the log lines are injected. Let's see that in action. So I'm not doing the live demo part. It's hard. Things go wrong. So that's why I will just show you that. But everything is, there's a link at the end. You can observe the code and run it yourself, even the simple application. So we annotate a function, ddlog. It's just doing something, sleeping to demonstrate. And the end result, we get all these parts are injected. Now we injected our instrumentation code. Now, basically, we have, and this is the end result of that. Now, when your function basically executes, you got your instrumentation. This is logs in that sense. So now go as annotations. I don't know, this would make old Java people happy or sad. Oh my God, I just got rid of these things and they strike back. I don't know. If you are an old Java person that writes Go, please find me. I would like to know. So, the grand plan. Compile time transformation. Now we have a way to hook into Go build time with toolexec. We know how to analyze the code, right? And then we know how to transform the AST. Yes, this is not runtime, so compile time. And we can modify and modify the source code and put that back into the Go build process, and the end binary will have our instrumented code. So this is zero overhead, but in runtime. So because we are actually, but in compile time. So there is an overhead in runtime because we are adding some code in place, right? So one more thing. Who doesn't like YAML? Please be honest. This is so few. Really? Don't you use Kubernetes? No? Okay. I hate YAML. Okay, but those directives, they're also not easy to add, right? You need to know where to add them, and there are some prerequisites. Maybe you need to add context. If this is a tracing code, you need to have the context.context, because context propagation, you need to have a span ID, tracing ID. There are some limitations as well. And still, we are dealing with some type of persona in Go community. They don't want to do anything. Yeah, I don't want to instrument my code. Even adding that command line, I don't want to do that. So how do we do that? Aspect-oriented programming. Have you ever heard about this term? Really? Okay. No one? Okay. I was expecting Brian. That shows your age, Brian. Sorry. So this is also very popular in Java, and it's about cross-cutting concerns, something that makes Java people happy again. What are those cross-cutting concerns? Observability, security, reliability. So anything is not your business logic, but you need to maintain and write and make sure it works in your code. Those are cross-cutting concerns. So we all gave examples from observability, but we can do the same thing for security, reliability, and performance. You can inject anything, right? This is the Go source code. We have, I will talk about it. Some integration, for example, it's for us enabling profiling on your production services. It's easy. Just let our compile time tool inject boilerplate code. So there are a lot of AOP solutions out there in Java, Python, decorators, meta classes, annotations. I don't like this stuff. Sorry, I don't even like the generics. So I am that guy, and I really core routines. What are core routines and iterators? Now we have. I don't know. Have you ever seen a iterator code? It's ugly. It's hard to read, hard to reason about. But apparently, they love it, Go team. Okay, that's another discussion. So our answer is like compile time transformation, no runtime overhead. We don't use any reflections, and like zero cognitive load for developers. Let's see some real-world examples. Of course, they are not real-world, but yes. Like, let's say we have a process order, we have some authentication things, we have some tracing, logging injection, like we decided to have a circuit breaker, and then boilerplate instrumentation code. With that, we can just like reduce everything to this. Okay, process my order. That's just the business logic. All of the things, I'm gonna inject that in the compile time. So you don't need to do that. How do we do that? YAML. Yes, this is the YAML part of that. So we have these definitions now. This is the thing, like I want to put an example, real life example. We have the join points. This jargon is coming from AOP and Java as well. So they call it a Java join point. And we have a directive, like an annotation. So it means like find all these like annotations and put this code in there. We still support that with this production tool, which I'm going to mention soon. But you can also do some other things, right? Okay. So you have a join point about like trying to catch any open file, and then you have a security library that checks whether if you can open that file, whether like, yes, basically sanitization, and just like you don't need to go in there, change everything. So you just basically say that any call to the open file, I would like to just like inject this and change that. So cross-cutting security concern. So I've been referring to this tool. It's called Orchestrion. It's a weird name, I know. I didn't know anything about this word before. So I call it the YAML vision realized in production. YAML strikes again. I was like, yeah. Apparently this is Orchestrion, right? It's some sort of an organ, like it's an old thing. I don't know who named, but yeah, it will become. So we named our tool from Orchestrion. And what Orchestrion does, it's compile time auto instrumentation for Go applications. So zero code changes required, OpenTelemetry compatible, supports bunch of Go frameworks, not just the standard library. It's production ready, you can use it with all these magics that we use. It's an open source project. How it works, you install that, there is a binary, and there are two modes, right? The first mode, we have the thing that we've been talking about. We can just like hook into, oh, this has a laser, no? Okay, doesn't work. Okay, so you can just say that, okay, you run this command with this mode, and I will do all the magic for you. The other way is, okay, you can just like pass it along to the binary. Yeah, it's whatever you would like to use. The most like the practical use case that I have, there is also a tool as like environment variable, and you can just set that, and basically you can build a base image where you set those environment variables, install Orchestrion, and then just like use that as a base container image, and all your Go images automatically got instrumented, right? Seamless. So if you're a platform engineer, you would love this, right? Okay, I don't need to deal with any of the developers, okay? I'm just gonna update the base image. Boom, I got the instrumentation. That's our use case. Like, so, all these were like simple examples. This is the sequent diagram of like Orchestrion. It's a bit more involved, right? There's this tandem between Go compiler itself and Orchestrion. I know, like, don't try to even read that. It's just, I just want to show that it's like complicated, right? We have a job server. There's a dance going on between like Go compiler toolchain and the Orchestrion. Okay, I have this file. Okay, I'm gonna manipulate the, I manipulated it. Okay, it's part of that package. Let's compile that package again. Okay, here the new package. And then you can link it, right? Like there's constant back and forth. It's the compile stage, then the link stage is the same. Now we have new packages because we injected some code and they have some dependencies. So here are the dependencies. Put that in your compile list or like the link list when you're getting everything together. No, we have new dependencies. So by that, what we are doing, like we wrote a bunch of integrations. What we mean by those integrations, YAML files. We basically wrote all those YAML files for you and put them in public Go packages, modules, and we have a Orchestrion.tool.go file. And this is basically a Go mod file. You say that, okay, I'm going to integrate that with that because I'm using Gin. I have some gRPC thing. I would like that integration. And when you have that file, Orchestrion finds that, finds the integration, just like Go module system, pulls that file, knows what to do, and inject every code. We already support like Gorilla, Gin, Echo, probably more. I didn't put everything, but if you have an HTTP application, you can just like use it and start like, if you have a service, start instrumenting everything. If you have a database, like same. If you have an ORM, we can instrument that as well. Now you can see that, okay, my application gets a request, I make a query to some SQL database. This is the amount of time that I actually spend in the querying, and these are the attributes, whatnot. We do that as well. RPC, same, and many, many more. So, but it's not just instrumentation, right? We have security products that, like, we use this to enable our customers because, like, yeah, they want auto-instrumentation, auto-magically everything. I would like to use your security product, and yeah, this is how we use it. Error stack capturing. This is what I've been working on for a couple of months. This is an interesting thing to actually think about. So even with the new like error changes, we don't have a way to capture the stack in place for the errors, right? So that would be nice to have them. Okay, this happened when this error happened, these were the calls. And then if we can put them in a span, and if you see that in the UI, okay, these are the actual like stack traces. You can say that, okay, I'm wrapping my errors everywhere, but the wrapping is not the same with the capturing the actual stack trace. So, but then this is an actual shotgun surgery. Let's say you've been using the standard Go package, but there are libraries out there that supports capturing the stack traces and propagating that. Now you need to change everything, everywhere, like all the error things. So we actually find a way using these tools, find a join point, find all the methods that actually returns an error interface, find that error value, and wrap that with this function, the package that we have, call this wrap function. And if there is no stack trace in that, we will just capture. Now your application, all of a sudden, like all the functions that returns errors, which is a lot of functions probably, can have this error stack traces. So the sky is the limit. If you can visualize that pattern in an AST form, and if you want, like, do you know what to change, you can do it, right? We have already predefined a lot of join points, like aspects to change to manipulate the code. It's YAML engineering, it's ugly, but you can do that. So the performance impact. We expect 10 to 20% more time spent in the compile time. There are some edge cases, but it's one-time cost. It only happens when you're compiling your program. I show you the complex, oops, okay, it's not like the complex diagram. We do a lot of stuff in the compile time. So compile times are a little bit slower. But compile times are not that expensive compared to developer time, so maybe that is acceptable. There is no runtime overhead, there is no magic involved. If you manually instrument your code base, it's the same result. And the binary size depends on the injected packages. It could be increased because you were like not instrumenting anything, you just like edit another module. It's the same thing. But you get automatic distributed tracing, metric, logging, all over your fleet, all the Go processes that you have. You don't need to maintain anything. consistent instrumentation across the team, production-ready observability, whatever you would like to call it, like business things. Like this is the value of observability, right? We are not discussing that. That's like it's about like how we put that in there. And the Orchestrion is agnostic to the library that it injects, right? If you have the correct YAML files, you can inject anything. If you have your favorite instrumentation library that you've been building in a company internally, you can use Orchestrion to inject all these things. Or you can just use OpenTelemetry SDK, whatever. Like the Orchestrion doesn't know anything about the injected thing. So we aim for zero developer friction, production-ready solutions. You can just use this by hooking toolexec, basically. I am sure Go runtime team or compile team, they are not happy with what we are doing, or all the community are doing. We are really abusing something they put there for maybe introspection purposes, right? Okay, maybe you will have a time function. Okay, use it. You would like to profile what's going on in between steps. Actually, like that's one of the best use cases. I think they are using it for that as well. Like, okay, how much time it takes to build that file and track that, right? It's useful for that. But it gives you a lot of information in those calls, like what is the source code? And yeah, okay, you got ideas. And this is the end result of it. So this way is different from the other languages, runtime magics, proxies, whatnot. First of all, it's predictable. There is a mode. You can actually say that, okay, Orchestrion, I don't want your magic. I want everything explicit. Just spit out what you generated, and you can check it in. That's a way. It's doable. So it's performant because there is no runtime reflection, whatnot involved. It got like access to the full AST. It can do a lot of stuff. Like sky is the limit. Like this is imagination. You are writing code. Whatever you can write, you can make this tool to write that code piece. It works with all the existing build system. Go. If you are using Bazel, I'm sorry for you, but it works. We also use that. So, but it supports. Like there's nothing wrong with that. So the feature, like what do we do from now on? So, a couple of months ago, Datadog decided to donate Orchestrion to the OpenTelemetry. This is a community project. This is already open source. So we just want to make this way more ubiquitous so that community gets an adoption. They can use OpenTelemetry. They can use any library they would like to inject. We just want to have there. But there are other people also came to same conclusion. There was a small project started in the OpenTelemetry contrib repo called inject, doing similar stuff, but in a very primitive form. And there was another tool from Alibaba called OpenTelemetry Go instrumentation. It works with the same way. So, and when this started, they also decided to donate the project, and OpenTelemetry being no kingmaker, okay, we are going to form a SIG, and you, both parties, build a new tool. So this is what we are doing. So there's an OpenTelemetry Go SIG working on auto instrumentation, compile time instrumentation. This is the first tool that I mentioned. It's retired. Now we are learning from Orchestrion, our experience, the tools of like Alibaba already built, and we are merging them together, and we will have like a neutral tool that does the same thing in OpenTelemetry repo, and CNCF gonna own that, and it will be injecting the like OpenTelemetry SDK itself. There is also a project that I would like to mention. It's called OpenTelemetry Weaver. It's about setting the semantic conventions. Basically, another YAML project. So you define your observability standards, semantic conventions, whatnot, and it generates the documentation, all the SDKs that you would need for Python, Rust, like Go, you name it, like for all languages. Then you grab those libraries correctly, like by semantic conventions, and you instrument your application. So you can combine these both approaches, right? You can use the weaver, generate all these things in a semantic convention way. It's just an application to inject, get that, use this tool, inject to your application. It's a couple of days of work probably to decipher all these things and put everything together for a platform engineer. But then like your whole services can have instrumentation, an up-to-date instrumentation, or like some security protocol that you would like to check. You can have it. The error tracking that I mentioned. So if you want to go into this, like start small, like pick a service, pick a demo application, compile with that, see the result. We have a, for example, Orchestrion diff command that shows you what it actually injects. Try to find some AST patterns that you would like to, if you want to do something custom, like, and try to inject that one as well. If you are like super hyped out for whatever reason, okay, that was the thing that I was waiting for. I want to contribute. We are like, you can find us in the public calendar of OpenTelemetry. We meet every Thursday morning, if I'm not mistaken. And we are at the beginning of the project, so you can, there's a like really tremendous amount of things to contribute back. So if you want to do something in open source, if you're like want to learn more, join the meetings and try to contribute. So this talk was there's a prequel to this talk. We've been building this tool for apparently 4 years. I only joined Datadog 6 months ago, so I wasn't there. So this talk from John Butner, it actually shows a primitive version of this tool. And if you want to learn more about it, check it out. It's a great tool, great talk. You would learn a lot about it. So thank you, everyone. This was all the content that I would like to share. I mean, it's your turn to unleash the toolchain. These are the slides, if you want to learn more. It's in a GitHub repo. There are also some links to the resources that if you would like to discover more. If you want to keep in touch, these are my handles. Apparently, Font Awesome 5 doesn't have a blue sky icon. So sorry about that. I need to upgrade my tooling to Font Awesome 7. My front-end skills are limited. So probably I will ask Cloud Code or something, okay? How do we do this? But yeah. One more thing, since we have time. Dark magic. Do you want to see some dark magic? All these things were magical for a Go developer. If you don't feel like it, I don't know. The first time I've seen this tool, before starting working on that, like all my Gopher senses were like tingled. What is this? Like, why do we do this? But the technical challenges are like really nice. So, patching to Go runtime. We can actually do whatever we want, including the Go runtime, right? Because when you say, okay, Go build -a, it builds everything. When it tries to build everything, it includes the Go runtime itself. So that means we can reach out to the Go runtime source code and do whatever we want. So this is the dark magic part. In the code that I'm going to show you, we are trying to modify runtime G, like one of the core components. And it's creepy, right? We can just like break anything, the whole thing. It could be unpredictable. Apparently it's not. So, but why we wanted to do that? So I show you that some of the functions, they don't have the context, right? And you would like to instrument that code. How do you do that? You need to propagate the context. You need to find the context. So we come up with a thing called Go local storage, dully inspired by thread local storage. And what it does, like, if we have a context in a Go routine, we capture that, put it in there, and then like we read it from there when we are executing the code because it's not properly passed along. So to do that, we patch the runtime itself. Runtime gstruct, we add another pointer field in there. There are some like functions that we add with Go link name, okay, add these things, and there will be a package that you're gonna be linking, and you can jump onto that and do the cleanup after Go routine exits. And the YAML part, okay. So with all those like join points, as like you are reaching out your own code, we say that, okay, find the Go run G time. Yeah, it just finds that struct definition. And at this struct field, that special name struct, type any, oh yeah, please import unsafe, because we are doing something really unsafe. And then we put a link name to link against that, add these functions to that struct, and now they are available. And then now we can use those functions to clean our mess. We also hook into the Go exit, and then like call a function to basically make it nil, right? Because it's not exiting. Or whenever we will call it again, we will inject something else. So this is the function. Like these are details, but if you are interested, they're in the slides, how we do that. By that, we implement a stack. Basically, we can push things on the stack, anything related to the context, and then we can, for example, put a tracing ID, put a span ID in there, and then if a function that we are trying to instrument, if it doesn't have a context, it can reach out to the Go local thread GLS, basically, and read that value like this, right? It's a GLS context. We put something in there, and probably it's the tracing ID, span ID, and voila, some dark magic. So yes, this time I'm really done. Thank you for listening.
All right, I think we have time for a couple of questions before the break, if anyone's got any.
Hi, that was great. Really interested to use this tool. Is it the case that you can see the generated code? I wasn't clear on that. So is it go directly to binary? Like, can you see the effective result of, as it were, as source code?
Yes. So you can. So whenever Go builds things, right, it creates a temporary directory, and you can actually see those generated codes. Maybe not the source code directly, but the artifacts, the archive files, they are generated. But we have a mode that you can actually observe them, right? And it's called Orchestrion diff, newly added. If you give there's a flag that you set, okay, Orchestrion, whatever you are doing, give me all the information you have, basically debug mode, and it gives you that, okay, while I'm building this binary, I generated this directory, and everything is in there. And you grab that directory in your source code and do the Orchestrion diff, and you see what were the results.
Right, so you could then just build that and you get the same effective output.
It's already built. If you see, like, this is just for debugging, right? It's just for transparency.
Right,
if you want to change something, you go back to the YAML file, change stuff.
But it is the source code that would produce.
Everything is on source code, yeah.
Thanks.
I think my question might be slightly similar in that regard. So you're putting the code you're going to inject in the YAML file, right? But then how do you go about testing that code?
Yeah.
So make sure, because I mean, I don't know you, but I very rarely get the code right the first try. So
we have some testing facilities. Basically, they are snapshot tests, right? Again, YAML files. We say that, okay, this is the aspects that I want to have in the YAML file, and this is the code template that I would like to inject, and this is what I'm expecting to see. We create those like golden files, snapshot files, whatever you would like to call them. And this is also necessary for the regression testing, right? And they get run whenever we change something. That's how we test.
In terms of being able to debug after you've run this sort of thing, so if the changes that have been made by toolexec or whatever, are they altering the file names, the line numbers of what you might come up in your stack traces?
Can you repeat it? I'm really having a hard time to also hear.
Question about whether when you're debugging, when you're doing toolexec stuff, is that affecting the line numbers, the file names in your stack traces?
Everything. Yeah. We also so we have a mode that we actually, everything happens in the compile time and all the line numbers are changing and accordingly we change everything, right? But let's say that you don't want to do this implicitly, you want to have something explicit, right? And there's a mode for that. I want to run the Orchestrion and I want to see all the outputs in my code base. And if I want, I would like to clean everything up, right? For those things, we inject some comments in place. This is where we started, like the line number, this is where we ended, and then when Orchestrion want to clean your source code, find those blocks, remove the source code, so you can go back. So everything is automated.
Any other questions? Got one over here.
Thank you very much. It was very interesting technically. You said yourself that you don't like things like annotations and,
I don't like what?
Like Java annotations and like that sort of thing, right? It seems to me that what you've kind of ended up with in terms of like the end result is something that looks very similar to the black magic that annotations do, except
we're exactly doing that, yes.
The difference being these ones are A, invisible, and B, like everywhere. And I just kind of, like as a new developer to a repo using this, like how do I like even discover that this black magic is happening and start to like reason with it?
Yep, I agree. So first of all, we started the talk by saying like we despise these things, and at the end we just like ended up doing the same thing. That's the irony of the talk, right? But like there are people out there, there are users, customers, they would like to have this, right? They don't care about it. Me personally, maybe I am working in the instrumentation space for too long. I would like to see what's going on, right? I would like to see and change everything. So being explicit is more important for me personally, but it's not the same. And I understand. I see in code like companies, they have thousands of services and too many teams and microservices, right? It was the hype topic. And if you want to change something in there, it's a lot of development time. And I understand their reasoning. They need it.
Hi. My question is about security. My question is about security.
Okay.
And did the Go team see this, or are we heading into an era where...
We have open issues already. We talk about our journey explicitly. We have meetings regularly, and they know what we are doing. And we also demanded some improvement in the toolexec, because some of the things like hard, especially when it comes to build caching and whatnot. They didn't say anything, the issue is open, so maybe we will have it someday. At least they didn't close it, so it's a good sign.
On the client side, or like on the implementation side, my question is, how can we, are we heading into an era where coding agents inject stuff into our code, malicious stuff into our code during the build time, and we won't even notice it? How can we prevent that from happening?
Can't hear, really.
How can we keep it secure at the build time when AI coding agents inject stuff into?
But it's like, you can always have the diff, like you can basically enable a CI step if you want, and you can just render all the changes that you have and do something about it. But it's like, there is, if you are developing this, there is no, it doesn't give additional attacks. It gives an additional attack surface. There's this, if they know you are using this, and if they change the YAML file that you are injecting, they can do stuff. But yeah.
Okay, I'm afraid I think we're about out of time there. So could we have another big hand for Kemal Akkoyun?
Thank you.